Before we begin with this talk, we must appreciate the entire Scala R organizing committee for this wonderfully thought about multi-time zone single day conference. They've done an awesome job and kudos to them for that. Uh, some things about me, as already told, I am working for HCL Technologies in Amsterdam. HCL provides digital services to its customers. Currently, I'm working on building a contact center application. When people think about contact center, they think in terms of hardwares or phone lines, but this is a fully digital contact center. We use programmable APIs to create voice, video, and chat solutions. I'm also available on GitHub, and you can find me by my name Ayush Works, and you can check out some of my open source work. So let's get started. Let's set some goals for this talk. By the end of this talk, we are hopeful that we will understand the concept of observability. We should be able to grasp what it means for a system to be observable. We should be able to appreciate why we need observability, especially in distributed systems. We will look at one of the tools of observability. We will focus on this tool. It is called tracing. We will understand some core concepts behind it, and we'll understand how they are to be used. And finally, because of this is a Scala conference and we all like Scala, we will look at how to do tracing with Scala, how to do tracing functionally using compositions. So these are the 4 simple goals for this talk. And now we can start. First, what is observability? A general notation or understanding in the community is that when you can use systems external outputs to infer its internal state, the system is observable in nature. That means you can gather the output that a system produces, and using that output, you can determine what might be going inside that system, how it is behaving the way it is behaving. If those patterns are shown by a system, it is observable in nature. So basically, observability is about adding visibility to your systems, making them more visible from outside without peeking inside. And a fair question next would be, why do we think we need observability in software systems? Well, as software engineers are reliable and as we are, we deliver products which we believe handle all scenarios. But as the system grows, as we add more features, as we onboard more users, software complexity will always grow. As the complexity grows, we will come across scenarios that we never thought about. We will come across use cases, problems that could not have been thought in the past. We could have never handled them because we were not aware of them. And this is a typical saying in the SRE models that system will fail. There is no denying this fact. So if we have to live with this notation that software systems will fail because they will grow and we will observe unknown things in them, what we can be ready for is a system that will fail, but upon failing, it is easy to debug. A system should be easy to debug and it should be easy to reason about. Now, this is where observability comes into picture. Systems that are developed using observability patterns are easier to debug and they are easier to reason about. If you come across problems that you have not seen before in your software, an observable software will make it easier to find the problem, to root cause the problem. Let us be very clear in one thing, that observability is not the same thing as monitoring. Monitoring is good in reporting the overall health of a system. You want to export graphs of CPU usage, or if you want to export number of HTTP requests, yeah, monitoring is good. But we know what we were looking for. We know we were looking for HTTP requests, we were looking for CPU data. So monitoring is useful when we know what problem is in hand, when we know about what issues we might be facing. It does not help us when we are trying to figure out the unknowns, things we thought are not possible but are now happening. How do we infer what is happening? So in that case, we will need observability and not monitoring. But that does not mean monitoring is redundant now. Monitoring is complementary to observability. Observability can be thought of as a superset of monitoring, but with observability, you get data that is contextual in nature, that has a causality attached to it, and is more enriched than data generated using monitoring. So the next topic is, how do we make our systems observable? There are various design processes, different thoughts. The consensus is there are top 3 tools that you can use. 2 of them are fairly common: logs, matrices, and the third one is traces. Each one of them has its own purpose. It has its own pros, and some of them also have their cons. They all serve their unique purpose, and they sometimes complement each other. The important thing in using these tools is placing them intelligently. If you put logs, matrices, and traces everywhere in a system, that does not help. You have to have intelligent placing. For example, whenever your software makes a decision whether to choose path A or B, maybe it's a good idea to put a log or a trace. Or for example, at the entry point of your software system, maybe it is a good point there to put a counter metric. So these tools are pretty common, but what is uncommon is their intelligent usage. So we must be careful in how we use these tools. Let's just have a brief intro of each of the tools. Logs is everyone's favorite. They are easy to generate. Most languages, application frameworks, libraries have support for logging. Matrices are also very common. Matrices are numerical representation of data which is captured over some time period. And because these are numerical data, it is easy to store them. It is very easy to process them. They are perfect for aggregating, and they are very easy to query also. So logs and matrices are pretty common when we talk about making a system more observable. But there is a drawback, or there is slight problem with logs and matrices, that they are not enough by themselves. The problem is with their scope. Logs and matrices are actually system scoped. By default, they provide you data from a system that they were generated from. If you are in a distributed system, or if you have multiple systems involved, then a single log line cannot tell you anything about other systems. If you are required to analyze an execution path that traverses multiple systems, and you only have logs and matrices from those systems, then you need to do an explicit join using some ID between these traces and logs. You need to do an explicit join between these matrices and logs if you want to get the whole picture, because each log and matrix belong to a single system. They will not tell you any information about other systems, and they will not provide you any causality data. Causality is the concept of why a particular event happened, what was it preceded by, and what will it be followed by. So that is what we mean by causality. And matrices and logs are not good at providing causality information. If I check a log line in an HTTP server, I cannot infer by that very log line that what might have happened before this log was printed, unless I do it myself in the log, but that's not something anyone wants to do. So seeing that log line, I cannot infer what happened before this, or what have caused this long line, or what might happen after this. That's not something that logs and matrices provide, causality. Uh, Things like causality, things like cross-system data are very important for distributed systems. Let's imagine a distributed system which contains three components, three subsystems. This could be three microservices which combine together to perform a single operation. Each microservice is an expert in its own features or its own domain. The three microservices combine together to serve a single request, with A being the entry point of the request. Interactions happen between A, B, and C. The microservice B internally also has a need for B1 and B2. These could be a database call or a Redis call that B is making internally. So we see that distributed systems interact with each other to serve a single request. Because of these interactions, there is an inbuilt complexity to them. You need to understand the details of A, B, and C in order to understand the whole system. Not only are they inherently complex, each system has its own tech stack, it could have its own language, and this adds to a level of unpredictability and uncertainty. Each system is also a single point of failure. We agree that to serve a single request, all three components, all three microservices are called. And suppose if one is down, then we get a failure in the entire request. So all these three are single points of failure. But this is something that we get with distributed nature. This is a cons, but there are many pros also. But what happens when distributed systems fail? We need to debug the issues in them. And debugging issues in distributed system is not the same as debugging issues in a normal monolithic. The known conventional methods of debugging systems will not help. We need some extra information in our hand to debug problems in a distributed system. Here is an example of a request coming from a customer to a distributed system deployed on the cloud. This system basically has a multiple services which interact with each other to serve the request. There could be tons of them. Some services are calling one only, some are calling multiple of them. Now, to debug a problem in the request, we cannot look at only the data of one service like service A or service B. We need to go beyond system scope data. We need data that lets us combine operations between these two services or more than two services. We need data that can be correlated. We should be able to tell that service B was called because service A got this information, or service B failed because service A called with a bad data. Things like that, that we can correlate between systems. So debugging distributed systems needs contextual data. It needs causality. Again, causality is important because there are thousands of services in a distributed system ideally, and you must understand at each event what caused it and what might happen after this. And that is causality. So if you have that data in your hand, it might be easier to debug a distributed system. Now, logs and matrices do not provide contextual data and cross-system data. They do not provide causality. So we turn into something known as tracing or distributed tracing. Before we look at how to use it, let's first things first, let's come up and let's understand some terminologies. What is a trace? In a distributed tracing system, a trace represents an execution path of a single request. Everything starts with the first request, and as that request travels through a distributed system, it generates a trace. So that is what is a trace. A trace is composed of one or more than one spans. A span is a primary building block of a trace. It represents a single unit of work done in a system. Spans have some properties. They have a name. They have timestamps attached to them. when did the span start, when did the span end. And they also have an important context attached to them, which is called the span context. The span context carries data across process boundaries, across systems. The data is carried using the span context. There are two important properties in a span context, namely span ID and trace ID, along with others. When you look at a trace, it might contain multiple spans, and spans might be nested or they might be ordered. And this nested and ordering represents causality. Let's understand this by a simple picture of a distributed trace. So on the left side, we have the flow of a request through a distributed system. And on the right, we have a trace for this request. So as the request flows through each system, system A, B, C, D, and E, as the request flows through, each system generates its own span. Now, what you're also seeing on the left side is that service A, when it is calling service B, this call could be through a RPC or an HTTP call, along with the execution data, along with the data to execute business logic, it also needs to pass the context information of span A. The same pattern is followed by span B when it calls C and D. So this context passing between the various systems is very essential, because on the right side, you see that span B is under A and span E is also under A. This nesting is inferred because context data was passed from A to B. If the context was not passed, span B would have no relationship with span A. So we were able to derive this nesting and this ordering because along with their execution data, at each point of interaction, services also passed context data, the span context or the trace context data. So there is also a term in tracing which is called an exporter. An exporter is an actual implementation that will record the spans and publish them somewhere. You might have heard of Zipkin and Zager, and they are very common known exporters. Now, who comes up with these standards or who comes up with this nomenclature? How does it all go? So there is a project called OpenTelemetry. It's a cloud native computing foundation project. OpenTelemetry is actually a result of merging two other similar projects, which were OpenTracing and OpenCensus. These two combined together, and they came up with OpenTelemetry. OpenTelemetry is currently in its beta stage, and it promises to be a one-stop shop for all observability patterns. It contains a set of standards. We just looked at the standards. It contains libraries, SDKs, and agents that provide observability. It has SDKs in various languages, and each language also has a set of exporters, which will actually capture the span data or the trace data and export it. And also there are UIs for each of the exporters. As of recently, it had a list of supported languages. To us, the interest is Java, JVM language, and there are many others like JavaScript, Go, Python, Ruby, etc. So OpenTelemetry promises to be a one-stop solution for all observability patterns. Now, we should look at some core classes of OpenTelemetry that define tracing logic. We will look at the Java SDK and the core tracing classes defined in OpenTelemetry's Java SDK. The first is the tracer interface itself. Now, tracer is an interface that allows for span creation and interaction with the context. So you have the interface itself. There is a method called span builder that allows you to create new spans given the name of the span. There is a method called with span that allows you to create a scope of a span. And there is a immutable current span that you can fetch from the tracer. Let's look at the very second important interface called span. A span interface represents a span. A span is created using span builder. We call the start method on span builder. Once we have a span, we can use methods to set its attributes. We can set attributes, we can add events, and we can also end the span eventually when we think it's done. A span has a very important immutable property called context, which is the span context. Let's look at the span context class from the Java SDK. The span context is very important because this is the information that we will use when we are propagating or when we are transferring context between services or between applications. The important attributes here are trace ID and span ID. For a tracing solution to be really helpful in a distributed application, we must ensure that span context are passed from applications to applications. If you do not pass span context between them, along with the actual data that you need, if you don't pass span context, you will not be able to infer relationships, you will not be able to infer causality, and then tracing is not that much of a help. So let's look at a very small example in Scala of how do we do tracing, how do we create a trace, and how do we create a span, and how do we publish a span. I am going to use the Java SDK from OpenTracing. So this is a very simple application, a hello world equivalent for tracing. We see that we have to grab a handle to what is called a tracer provider, which is an SDK provider. Once we get that, we can add span processor to it, which is what line number 10 does. A span processor determines how your spans are processed. Basically, you are defining what sort of exporters you want for your spans that are created using this tracer provider. In my example, I'm using a Jaeger RPC exporter to handle my spans, and I'm providing a name to my service also. It's called my service. Once I have attached the processor to my provider, I can create an actual tracer instance. I can get it by providing a name. If it is there already, it will fetch this tracer. Otherwise, it will create a new tracer. Now, using this tracer, I can create spans. Once I have a span, I can set their attributes. I can end them. I can create child span from this span, and so on and so forth. So this is pretty simple of how you can create a basic trace using. If you want to get started, this is how you will do it. It's pretty straightforward. There's nothing complex here. Now, this is simple, but our code base, the code that we work with every day, is not simple. If you want to introduce tracing there, you will have a lot of challenges. Any production worthy application that wants to do tracing will have the challenge, and the biggest challenge will be context propagation. Applications will have HTTP calls, they will have TCP calls, and as these calls are made in different threads or in the same threads, you want to make sure that the spans that are created are relatable to each other. You can link them together. To link them together, you need to pass this context from one place to another. Now, that is the first challenge when you introduce tracing, how to do context propagation. The second challenge is that you should make sure that tracing logic does not pollute your code. It does not overtake the actual business logic. You would want to make sure that these two are not mixed up. So let's tackle the first problem about context propagation. Again, I want to focus on what is context propagation. We have a system, suppose, which is composed of three services, A, B, and C. The entry point is A again, A calls B. B internally has a dependency to two subcomponents, B1 and B2, and B also calls C. Now suppose a single request is served in this manner. It comes at A, information flows from A to B, B calls B1 and B2, B also calls C, and that is how a request is finally served. Now, if you want to see a trace for this request flow, we have to be very sure that we pass span information between these systems and within the systems. So there are two kinds of context propagations. First one is across system. That means when service A is calling service B, let's assume it's an HTTP call, along with the other HTTP data that it must be passing, it must also pass the context information that it has right now. If a span is created at point A and a span is created at point B, they must be linked together in order to make a meaningful trace. That means system A must pass context to system B. So that is cross-system propagation. How do you propagate data from A to B? Now, OpenTelemetry provides a solution for that. They have a concept of propagators. Propagators can serialize and deserialize the context into a concept known as format. So at point A, you can serialize using a propagator and convert the context into a format and send it along the wire. An example for a format is a HTTP format. So you can attach the context data in form of HTTP headers. And at service B, you can deserialize them, create a span out of the context, and then continue forward. In this way, both span at A and B are linked to each other. So this is how telemetry proposes to solve cross-system propagation. What we are more interested in today's talk would be within system propagation or in process propagation. That means when we receive the request at B, and B is a service written in Scala, and B is calling B1 and B1 is calling B2, where B1 can be another service and B2 can be a database. We also want to generate spans at points B1 and B2, and we want to link them to the span created at B so that it can be linked to the overall request that came at A. So in process propagation is how do you propagate tracing data from B1 to B2? And this is what we'll try to solve in this talk. So OpenTelemetry proposes two solutions for in-process propagation. The first one is the implicit or the automatic propagation. In this implicit or automatic propagation, you use techniques like thread local to store the context information in memory somewhere and then retrieve them as and when required. Let's try to understand with this some Scala code. Let's try to do implicit propagation using Scala. Now, suppose you want to create a span for some unit of work. Now, the unit of work that you are doing is represented in this function by the variable do work. This is some unit of code that you want to generate a span for. Here it is a by name parameter. So how do we do this work and how do we create a span for this work? So the span must be started before the work is called and it must be ended after the work is done. And we should also be able to capture data from the previous spans. Whatever span we create when executing do work must be linked to the previous span if it is already present in the system. So how do we do that? Using implicit propagation. So what we have is we have a span builder which has a method called set parent, and using this method you can set the parent of the span that is about to be created. How do we get the parent? This is implicit or automatic propagation. So we use a method called tracer.getCurrentSpan. What tracer.getCurrentSpan does it gets the span from the context. Now, how does it get the span from context? Who must be setting it? So what happens is there is a method called tracer.withSpan. Whenever withSpan is called with the span, this span is set in the context. So in our case, what we are doing is we are creating a span. We are getting the previous span from the context, setting it as the parent of this new span. Now in our scope, we are going to set the newly created span in the context. So any code after this line, especially in the do work, when it calls get current span, it will get our newly created span. So we create a span using the previous context. We set this span in the current context. We do our work. And at the end, we need to make sure we close the scope so that the context is reverted back to the previous state. And we must also do a span dot end. So this is a simple technique of how you can do implicit propagation of spans with OpenTracing in Scala. Now let's look at a very simple code base that actually does this. We go from top to bottom. We have a root method which is internally calling two methods, which is internally calling only one method, method A. Method A internally calls a method B. Now we want to generate spans at each point. So we generate a span at a root method. We call the span name as root. We generate a span at method A. We call it as A, and similarly at B. Now our trace function ensures that the context of the root span is passed from root method to method A, and similarly the span created at method A is passed at method B. That is ensured by the tracer.withSpan scope method. So if I run this code and if I have the tracer set up with the correct span processor and I'm using Jaguar for my example, I will generate a tracing UI like this. So we'll have a root span. Root span will contain inside it a span A, and span A will contain inside it span B. So by looking at this very simple trace, we can infer that span A is inside root span and span B is inside span A. But this was a very simple example. Rarely in life you will have chances like this. This is Our systems are more complex than this. Our systems have asynchrony. Our systems are asynchronous in nature. They do parallel calls. They have parallelism. They are multi-threaded, obviously. So asynchronous code is the normal way of working. We have futures. We have effectful libraries like Zio, Cats Effect, Monix. And if we have code bases that are full of these, then implicit propagation will not work, because implicit propagation works on the basis of thread locals and storing data in the current context. And obviously, if you are using libraries like futures, or if you are using cats or Zio, this technique is not going to work. Now, we need to solve this problem for our asynchronous code, which is the use case most of the time. Asynchronous code is the normal way of working. So for that solution, we have another method that we need to manually or explicitly share the tracing data between methods or between services. We need to propagate the tracing data manually. That is, the span information must be passed between methods as method parameters. So in order to understand how this can be done, manual propagation, let's look at an example of a synchronous code. We will look at a user registration service. This service basically has a feature of registering users in our system. The starting point is the register user. It accepts a user and then it calls another service which is add user. Add user internally saves the user in a database, sends the user a welcome email, and upon that it notifies the downstream users of this new user, that a new user has been added. Now, if we write this code, which is production worthy and which is fast in its nature, we will use some libraries which are effectful. We might use Zio, we might use Cats Effect, we might use Monix. For my example, I'm going to use tagless final with cats effect, but that is just a choice of which framework you want to use or which library you want to use. The fundamental ideas do not change. So here is how I would represent that service in my code. We will go from bottom to top. We have the entry point as register user method, which accepts a user. Register user is actually going to call the save user followed by the notify. The save user is actually saving the user in database and sending him an email. Now you must notice that database save or sending an email are side effects which must be wrapped or which must be suspended in the proper type, because as Scala programmers we want to write pure referentially transparent code. And for my talk, I'm going to just use tagless final with a sync class from cats effect, but the same concept hold for any other effect library as well. So the code is pretty simple. Register user calls save user, and save user calls db save followed by send email. And after saving a user in our system, we notify others of this new user. Now suppose we want to introduce tracing to this code. Our goal is that we should be able to see traces for register user method. We should be able to see traces for save user and for notify. Not only do we want to see traces for them, we also want to make sure that these traces are related. We want to make sure we can see in our trace without looking at the code that the register user method internally called the save user, and the save user was followed by a notify. We want to see that information not by looking at the code, but by looking at trace, because our systems are observable in nature. So let's give it an attempt, and we'll use explicit or manual propagation. I'm going to explain a method which is going to create a trace at any given point. How does it create a trace? We'll look through it. So creation of a span like this, tracer.span builder.name.start span. This entire line or this entire thing is a side effect. And as Scala programmers, we want to wrap or delay those side effects in proper types. So I'm going to use the delay method here to delay creation of a span. I'm also going to wrap the ending of a span in a delay. So this is because the span creation and span closing are side effects. That is what we have done. Now every span that we start must be closed. So this is like a try with finally. And for that, I'm using the resource class from cats effect. It basically allows me to create effectful. This is an effectful acquisition, and this is an effectful release of that acquisition. So the semantics of resource guarantee that the span will be ended no matter how this resource is used, in whatever way it is used. So this is how I will create a span at any given point. And you can also see that to create a span and to create a meaningful span, I must set the parent, and the parent span cannot be implicitly guessed. It has to be passed manually to this method. So the parent span is passed as a method parameter. It's time to use this method in our code. So here is our code, register user. It is calling. Let's look at the register user method. It is calling the method trace. It is passing the name of the span that must be created. Along with it, it is passing the span that must be the parent of this span that is created. And we get this information from a method parameter. So now when we call register user, apart from the user, we must also pass the parent span. So the register user method creates a span using the trace method. The newly created span is then passed along to child methods like save user and notify. The save user and notify methods do the same thing. save user again creates a new span called save user, and the parent span is provided as a method parameter. It performs a DB save and an email send. Notify also creates a span. It's called by the name notify. It also gets the parent span information as method parameters. The span that is created by the trace method can be used to pass the span to child methods like we are doing here, or it can be used to pass span information in a remote procedure call or HTTP calls. We can do anything with this new span now. So this is manual propagation. We are explicitly passing the span from one place to another as method parameters. And of course, we will generate a nice trace. We will have the register user at the first. Register user is having two spans under it. One is the save user span, other is the notify span. So this causality is very easily inferred from this UI, that we can see that save user and notify are part of the register user process. What is also noticed is that notify follows save user. Only once the save user is done, the notify is called. If for some reason save user fails, the notify is not called. And that information can be inferred from this UI without looking at the code. So which is good for us. So we achieved some sort of tracing with our asynchronous code. But what did we have to pay for this tracing? What cost did we pay? Well, if you look at our code now, apart from business logic, we are also having tracing logic mixed with it. Ideally, notify method did not have a requirement for anything called as a span, but now as an operational concept, we have to pass parent span because we need to generate traces. So this business logic is getting mixed with tracing logic. And that is a drawback of this manual propagation, that your code is getting polluted with tracing logic everywhere, and business logic might be overshadowed. So maybe there is a technique to make this tracing information less visible, or even though it is explicit, make it less explicit in nature. How can we do that? Let's look at a better approach. So Scala is a language which is rich in its types. We must use its type system to help us. There is a particular type class here that will help, and that class must be familiar to you. It is called a Cleasley or a Cleasley. A Cleasley is not present in Scala standard library, but it is present in other open source libraries such as CAT, Score, and others. What is a Cleasley basically? I have taken this definition from CATs, but the principles are same. A Cleasley is a wrapper for a function that takes a parameter a and returns an f of b. It basically is a wrapper for a method that takes a and returns another value b wrapped inside a container. Now the good things about Cleasley is that if the container composes, then the Cleasleys also compose. And this is how you can see they compose. Obviously we need the container to compose. But if the container does compose, if we have a flat map instance for the container, then the Cleisleys themselves will also compose. This can be made easier by example. Let's assume we have two methods which are called safe square root and safe reciprocal. Safe root basically determines the square root of a number, but it is safe so that if the number is less than 0, it returns an error. And we are using the either effect to represent the error case. Similarly, we have a safe reciprocal, which does a reciprocal of a input number. If the number is 0, obviously there is no defined reciprocal, so that is represented by an error in the either left. So these two functions, safe root and safe reciprocal, they do not naturally compose. I cannot call safe root followed by safe reciprocal directly, because this one returns an either, with a string on the left and a double on the right, and this one takes a double as an input. I can make them compose using pattern matching on either types, but there is another way. I can use classes to make them compose. And what I can do is I can write a safe root reciprocal method. I wrap the root method in a classly, and then I compose it with another classly, which is the safe reciprocal classly. This entire operation is basically composition of two methods that were not earlier composable. And when I pass a parameter that works for both the methods, for sure I get a right of a result. If any one of the parameters is incorrect due to square root or reciprocal, and if it fails, I get a left. So this is just a very small view of how awesome classes really are, and they are ubiquitous. You will find them pretty much everywhere in any important library. And here's what I want to say, that we can use the Scala's type system of classes to make our explicit propagation better. How do we do that? Let's take a look. So what does each trace point do? So each tracing point basically requires a parent span to be present, and we are passing it using method parameters. Another way to think about this is that any method that was earlier returning an f of a, sorry, this is not clear, this is an f of a. So any method that was returning an f of a and requires tracing can now be thought of as a classly of f comma span comma a. So it requires a span, which is the parent span, and it will return an f of a. So any method that was earlier returning a f of unit or a IO of unit or a IO of user is now basically, if it needs tracing, it is a classly of f of span comma a. Let's rewrite our methods using the same concept of classlies. So this method is pretty much the same, the start span method. It basically creates a safe span. You provided a name of a span and a parent span, and it uses the resource class and the delay to delay the side effects. We provide a type to our classly. We call it a trace. It basically is a classly of f of span a. And what our trace method does now is it takes an operation name, the new span that has to be created, this name. It also inputs a current trace that must be executed. This represents the current trace that must be executed using the span that we are about to create now. And the span name is this. So it has two input parameters, name of the span and a current trace that must be executed. Now to execute this trace, you need a span. How do you create a span? You create a span using start span. The parent span will come from somewhere, and because it's a classly, it will be there when it is actually called. We can assume that whoever is calling this will provide me a parent span. I will create a child span from this parent span, and I will use that child span to run my current trace. So this is how you can create a trace method using a classly, and you can assume that things will work because classlys are composing. The past trace will run with the correct child span, and the child span will be created with the correct parent span because this is returning a classly in itself. So anybody calling this will get a trace back. He will have to supply a parent span to run this. We will use the parent span to create the child span, and we will use the child span to run the trace. So here is a look at our final code base. If we use a trace type, again we go from bottom to top. The register user method, instead of returning an f of user, now returns a trace of f comma user. That means it is expected to input, or it is expected to run using a span. It creates a trace. and then it does its normal business logic. There is no span passing going around here. The methods have gone back to their normal signatures. They are not passing spans around, but the return types signify that you need a span to run them. So the wherever we have a need for creating a trace, we can call the method trace. We can pass it around, and it all works because our Kleisli is composed. So this is one improvement that we can do to explicit passing. We are manually propagating the span information, but it is slightly less obvious because we have made it pretty clear in the return types that to run this block of code you need a trace. If you pass a trace, you will be able to run this method, and we use that pass trace to create a trace, and the underlying methods work in the same way. They pass the trace around and it all works fine. So again, if I run this code using a Jagger exporter and a Jagger UI, if I see it, I get the same information. But the code is a little less polluted with tracing logic, and at least we are not passing the span information as method parameters. So a further improvement on this code can be that we create an effect class like the sync effect class. We also create an effect class which has a span information, and we can provide Kleisli's instances for those classes for that effect class. And it is not that nobody has thought of it before. It is already pretty well implemented in an open source library called matrices. It is using OpenTracing standards, but it is based on the very same concepts that we have discussed so far. If I rewrite my code using this, then I get a code base like this. It provides a trace type class, and that trace type class allows you to create spans. And there is a Kleisli implementation or a Kleisli instance for the trace type class. And at the end, I can call this register user method, and I can pass the Kleisli and run it. So this is one next step to making your code better, even though you are doing explicit propagation. So final thoughts after this long talk. Observability is something that is very necessary for distributed systems. You will need it if you want to build a reliable and resilient software. These patterns have to be baked into your code. This is not something that you can leave out of your design or of your thought process. It is not an ops thing. You have to do it as a developer. You have to bake these patterns in the code. Tracing solutions will help you in making distributed systems easier to debug. They will help them make more observable. And intelligently written code will ensure that tracing logic does not mix with business logic. I think I've run out of my time now. So thank you, everyone. This is the end of my presentation.